Yes, good afternoon, everyone. We are very happy today to have Professor Fumi Yoshida give us a talk on her work. Fumi-san, when she after she just graduated from Kobe University, getting her PhD degree, she came to Taiwan to our institute, as a postdoc, and she did very interesting work here. And I was extremely unhappy that because she left so early. She was supposed to be here forever, but she, she left. She left half a year and returned to NOJ. I was really sad. I was very sorry. And so now she's a professor at the University of Occupational and Environmental Health in Japan, Department of Basic Sciences, and very active in teaching and also in research. And she's involved heavily in the space project called Destiny Plus, which is going to the which is a small spacecraft flying by the comet, I would say asteroid, the Phoebe, and which is supposed to be the parent body of Gemini, which is a very interesting target. And but she has also spent a lot of time on Subaru, looking at their images, the results from asteroid research. So today we are very happy to have her to tell us in detail what her newest results. Fumi-san, please.
Yes, thank you very much for inviting me to speak this seminar. Today, I'll talk about our survey observation using Subaru telescope. Okay, this is just outline. So I introduce some structure of the solar system, then summarize our current knowledge of outer solar system. Then I introduce two kinds of survey, Hoshida survey and the Planet 9 survey. So this is, I think you are already, all of you know the structure of solar system. There is many kind of small bodies in the solar system, but not mixed up, but they have a group. From inside near-Earth asteroid and the main belt asteroid, and Hilda and Jupiter Trojan, and between Jupiter orbit and Neptune orbit, there is a center one, and the outside of Neptune orbit, there is a Kuiper belt and small blue square is comet, so comet is everywhere. And we investigate the solar system for a long time, and the solar system gradually expanded. So we try to find distant objects and more and more. So recently we found very elongated, very distant objects. So now we know that beyond the Kuiper belt, there is some or many detached objects. And the farthest structure of solar system is old clouds. So that solar system is the size of solar system is about 100,000 AU. So dense of observation and theoretical work reveals that current solar system something like this. So first that sorry. In the theoretical model, it predicts the planetary formation of in the solar system. So first, in the primordial solar nebula, there is that planetesimal forms, different kind of planetesimal forms in the solar nebula. Then planets start up that planetesimal, and after the disappearance of the solar nebula, again planets orbit shifted a little bit, then scattered a lot of solar planetesimal in and outer. Then current solar system is like this. So, and the right panel shows that current the complicated structure of the trans-Neptunian region. So we think this is this structure was a remnant of the era of planet migration. So the present icy world may be mixed of many different kind of planetesimal from the different formations site. So this is we are thinking. And we also know that there is a many kind of taxonic type of small body. And in the asteroid belt, there is a SCEMV type or something like this. And in the outer Hilda and Jupiter Trojan, there is only D type, P type, and C type. So we think that different taxonic type means that different material. So this difference of spectral type is evidence that the material differ between the inner solar system and the outer solar system. And we also know the size frequency distribution of each solar system bodies group. So we found that the size frequency distribution gradient extended from the asteroid belt to Jupiter Trojan. It became flatter. Then, meanwhile, the New Horizon space mission found that size distribution of crater on the surface of Pluto and Charon. They are flat on the approach. So this gradient approaching to the shape of the size distribution of crater on the Pluto and Charon, probably. So this may suggest the population of Kuiper belt objects having a flatter size distribution fell inwards, then added to Trojan group and Hilda group till outer main belt, outer asteroid belt. So we guess like this. So what we have now, that all theoretical model and observation evidence, all observational evidence supports the planet migration. Then from what we want to know from now is we want to know the detail of planet migration. Then how we can get such kind of detail. That's our observation focus on the icy body. Icy body are needed to answer the above questions. So now we try to do some find more icy objects. So I see objects relatively far away. So we need to use large telescope. Then there is several telescope looking at the northern sky, Pan-STAR and CFST and SPAR, and the southern sky, dark energy surveys telescope is looking at. And the LSST, Legacy Survey of Space and Time at the Vera Rubin Observatory, that's the most powerful survey telescope. The aperture is 8.4 meter, and they have a plan to do all sky survey from the Chile, but this is still under construction. So I heard scientific operation will start next year, but that the corona disturbed 2 year construction. Maybe that the science operation will start in 2025, maybe, but I'm not sure. So using this kind of 8-meter telescope, we can find the main belt asteroids larger than a few hundred meters. Jupiter Trojan larger than 2 kilometers, and Kuiper belt larger than 60 kilometers. Then let's introduce our survey observation. The fossil survey and Planet 9 survey, both are being conducted at Subaru telescope and Plim camp. So because we use this instrument is this combination of instruments capable of the deepest survey observation in the world. So large aperture and very sensitive CCD and relatively larger field of view. That's the point. So then I'll introduce fossil survey. So this is a fossil is acronym for formation of the outer solar system in an icy legacy. So it's an attempt to explore the history of solar system by excavating fossil of past evidence, past events through observation. In particular, we will investigate the icy world of outer solar system, which is not yet fully explored. So we have an international team and many co-I from Taiwan and China. We now our member is 36 people. Then where we seek out the fossil, it's we look at the outside of Hilda group. Inner part is the world of rocky and hydrogenous minerals, and the outer part is the world of ice. And Hilda and Jupiter Trojan are boundary between both worlds. So information of the boundary region is also very important to find the extent of the planetary migration. So what period of fossil we can do we seek out? So from our current observation of solar system, we cannot directly observe events that occurred in past, of course. So So we can only look for the trace of past event. So we fossil explored after the era of planetesimal formation. The size frequency distribution of TNO is believed to retain the initial size signature of the home planetesimal at that distant planetesimal disk. So information on the extent and degree of large scale of mix of the planetesimal due to the planet migration should remain the current Jupiter Trojan, Hilda, and TNO. So since above process commonly occur during the planet formation, so fossil can understand the universal planetary formation and evolution in the universe by understanding the detail of solar system formation. So fossil survey started in May 2020. We observed this field despite being disturbed by COVID-19 and bad weather. So the February observation found two first rotator candidates, but we haven't we have to expect it first rotator in TNO group. However, the subsequent bad weather condition, we couldn't follow up observation. So now this first rotator candidate are lost. So we are calling our observation in fiscal year of 2020 is fossil 1. So this is the number of small solar system body detected from fossil 1 data. So we found many small body of different groups. So what we are trying to find out first with fossil 1 is the bulk density of the small bodies population. So since the planet formation is history of collision through the process of collisional accretion and collapse, small body of certain size are expected to have a rapid structure. If the rotation is slow, the small body can maintain its rapid structure. But if the rotation rotate fast than a certain limit, so centrifugal force overcome gravity and the body deform into the very elongated shape, then eventually collapse. So this is a relationship between spin rate limit and light curve amplitude and bulk density. So once spin limit and amplitude of light curve are known, bulk density of particular population can be estimated. So relationship between spin limit and amplitude and bulk density of main belt asteroids has been well studied. So spin limit is about 2 hours. Then bulk density estimated from this spin limit is 3 gram per cc. So this is consistent with the idea that rocky debris is loosely assembled to form a single body. But yeah. Okay. Then fossil investigate the Jupiter Trojans. So fossil 1 detected 1,241 Jupiter Trojans and determine the rotation period of 53 Jupiter Trojans. From this figure, the spin limit of Jupiter Trojan seems to be 4 hours. Then estimated bulk density is 0.9 gram per cc. So this is a good agreement with the Patroclus by bulk density estimate from the binary system. So this value supports the idea Jupiter Trojan is the IC-dominated level pile. So fossil also investigate the Hilda group. So fossil 1 detected 315 Hilda asteroids and then determine the rotation period of 17. From this figure, the spin limit of Hilda seems to be 3 hours. Then estimated bulk density is 1.5 gram per cc. So fossil finds that the bulk density of small body gradually decreased from inside to outside. So this can be predicted from theory, but the fossil's determination of the bulk density value from observation is also very excellent result. And we will start the fossil 2 from next year. So this survey is dedicated to discover of classical and resonant TNO. So we observe this area, and observation schedule is like this. So resonant TNO is the object in the mean motion resonance with Neptune, and the classical is here, so you can see the figure. Then I'll explain why we concentrate on classical and resonant TNO. So in classical, there are 2 groups of objects, cold and hot. The cold orbits are circular and have little inclination from the ecliptic plane. And while the hot orbits are with high inclination and or high orbital eccentricity. So, and the cold has many red objects, and there is no large object. And a lot of binary exist in cold group, and hot has less red object, and there is a relatively large object and few binaries. So based on these characteristics, cold are believed to be planetesimal that form in the early system at the present position of more than 40 AU. So in other words, observed cold population is observed the icy planetesimal in the planetary disk, protoplanetary disk. To resonance, so people say that the current observed resonance zone is stable at the solar system age, and the resonant TNO fall out the resonance with time due to the chaotic diffusion, but the much slower than dynamical lifetime of scattered TNO. So we can think that resonance have not moved from the location of protoplanetary disk when Neptune settled into the current orbit. So therefore, the number of TNO in each resonance give information on the protoplanetary disk mass as a function of distance. And the average color of each resonance gives the information of gradient of this disk composition. So our plan is fossil to concentrate on the increasing the number of discovery and determine the orbit and of classical and resonant TNO. Then in fossil 3, we will observe their color. So please visit our website and you can see our survey's progress. And next, I'll introduce the Planet 9 survey. So we are looking for Planet 9. So after the Batkin and Brown published a paper in 2016, they approached to the Subaru telescope and established a research collaboration with us, as mean Japanese colleague. Then observation start from the September in 2016. So what convinced Batkin and Brown that there is a Planet 9? It's the orbital distribution of detached population is not uniform. So at first, the Trujillo and Shepard noticed perihelion argument for distant TNO make a pronounced clustering around around zero degree. Then Batkin and Brown began their study to reject the clustering claim by the Trujillo and Shepard. But after the analysis of data, Batkin and Brown convinced of the existence of clustering. However, the authors member have doubted Planet 9 based on their simulation and their survey observation. So more research needed. So in this figure, the showing the orbital distribution of detached population discovered to date. So in this figure, the direction of the sun to perihelion of each individual object is indicated by arrow. And you also notice that dynamical lifetime of detached object is shown with a different color. The purple is stable, the green is unstable, and the gray is between. The number of detached increased as observation progress, but the clustering is visible in the perihelion direction. So the Planet 9 hypothesis still remains. Then this is the latest Planet 9 orbital element predicted by Batkin and Brown. So it changed a bit from their initial prediction, but only a little bit. The mass become a little bit smaller, and the inclination gets a little bit small, but mostly not so different. Then anyway, we began search for planet 9. So expected sky area is shown in the black color. So you can see that left panel. Then other area, other colorful area are known from the other survey to have no planet 9. So that's why Subaru only need to observe the black area. Then, then we started observation like this, and we are observing, and Mike and Constance are looking at our. Okay, and so when we observe with Subaru telescope, we can find many moving objects like this. So, do you see that there are many moving objects in this field? So this is only one CCD chip. So there is a 10 to 20 moving objects per CCD chip. So nearly 1,000 moving objects in one hypersplenical field of view. From these many objects, we have to find the objects that match the motion of the planet 9. Then image processing and data analysis can be done almost automatically up to the cataloging. We use the generated catalog by pipeline to search for the moving object in these two ways. One first method is moving velocity range assumption method. So in this method, search is conducted assuming the speed of which planet 9 is moving. So first, we remove from the catalog star and from the catalog star and galaxy that they are not moving. Then exact pair of the light source and that conform to the set speed range from the day 1 and day 2 data. Then find if there is a light source corresponding to the speed in the day 3 data. Then visually inspection of moving light source done by our eyes. So far there is no object have been found that move like planet 9. And another way is RGB method. We call this is a method trying to find the planet 9 with our own eyes, not rely on the catalog. So overlay the image of the small same field to create a master image. Then subtract the master image from each image. And then overlay the image with red, for the first day, and green for the second day, and blue for the third day. Then we can create this kind of figure. So you see the right side, 3 green dot that are main belt asteroids only detected on day 2 data. And left side, there is a TNO. TNO's motion is slow, so the TNO remained 3 days in the same CCTT. So day 1 and day 2 and day 3, you can find the red dot, green dot, and blue dot. So if the planet 9 was found by this RGB method, it would be like this. So red, green, blue dot is narrow interval. Yes, but this is just I made it. so far, no object has found that move like the planet 9. So planet 9 still not found, but the survey, we continue survey. We need to find more objects through observation to get a full picture. So continued observation is necessary. So Mike Brown said that only the way to confirm the existence of planet 9 is to conduct a survey of outer solar system. And the only way to reject the existence of the planet 9 is continue the survey of the outer solar system. Yes, sir, we will do that. So the exploration of the outer solar system has only just begun. So fossil survey and planet 9 survey will continue to explore the icy world from now. And so I hope we can bring amazing discovery to you. So thank you very much for your attention.
Yeah, thank you so much, Fumi-san, for updating us on your work on Subaru search for Planet 9. Any question from the audience? You can either write down your questions or comments or raise your hand to ask questions. I have one question first. You said that you find some fast rotator candidates.
Yeah, in TNO, yes.
And how fast is the period, the rotation period?
Oh, this is actually Charles found it. The period is 1.7 hours, and another one is 4.5 hours.
Oh, that's very fast. And
yeah.
So for the density should be large. I mean, it's rubber pi.
Yeah.
And even for S-type bodies, even for asteroids, it's very fast rotating.
Yeah.
And how big are they? How big?
How big?
How big? Must be big. I mean, it must be tens of kilometers.
Yeah, that's big, but the apparent magnitude is 25 or something. Anyway, that's more than 60 kilometers.
Right. So therefore, usually in the asteroid belt, for the fast, super fast rotators, we talk about only objects of about 2 or 3 kilometers already. It's very large. So you're talking about huge fast rotator, super fast rotator here.
Yeah. Of course, we want to confirm, but we couldn't.
Yeah. And so you're going to continue the search, right? The observations.
You mean the light curve?
Yeah.
It's very difficult. So light curve needs a lot of time. But the fossil member want to find more objects.
And you think the SST would be able to help?
That's help to find a lot of objects, but not for light curve.
Okay.
Yeah.
Yeah. But how about Planet 9? Would it be able to search for Planet 9? Because it's also
No. Because the Planet 9, they also want to survey a huge area. So there is one possibility is New Horizon KBO survey. Today I didn't introduce because the shortage of time, but that survey it's the purpose of that survey is to find a very, very distant TNO able to observe from the spacecraft of New Horizon.
Yeah, from New Horizons.
So we took the same field image for half night every day, half night. Then 100 image, we got 100 image of the same field. So if we find a very fast rotator, we can detect. Yeah, we can investigate such kind of thing. But only one, two fields. It's I don't know how is the probability to detect such fast rotator in two fields. But
And and how about centaurs? The centaurs, you observe about 30 of them, right?
Yeah. You mean this one?
Yeah.
Yeah. Yes.
And you have their colors.
No. In fossil 1, there is no color observation. We will do that fossil 3, but not fossil 1. Yeah, that's unfortunately.
Okay, I would like to ask the audience if you have any audience, anyone you have questions for Fumi. Fumi-san is a very, very good opportunity to ask her questions. Because I see here a number of experts who should have questions. They're very silent. Zheng Yiqi.
Hi.
Yeah, you have a question for me?
I'm curious about how about the program in 2024 or 23. Yeah, you have mentioned you want to measure the color of the solar system body. So because the filter exchanging time is very long for HST, HSC. So what is your observation strategy? How do you design your observation?
In fossil?
Can you hear me?
Yes. You said
I remember in the earlier slide you show the future plan for this program.
Future plan.
Yeah. And you
this one
mentioned the color measurement in fossil 3.
Yes, so I want to do that, but still we have to submit proposal. Yeah, Hoshir 1, we got observation time for Hoshir 2, but so next year we have to submit a proposal.
Yeah, but is it not efficiency to do the filter exchanging using the HSG?
Yeah.
So how do you? Yeah, please.
Half night continuously one filter. And
I see.
Change to other.
Oh.
Yeah.
Yeah, I see.
And
so the main.
Go ahead.
So the main objective for the first 3 is to determine the color.
2023.
Yeah. 2023. Yeah, I see. Yeah.
We don't because that we didn't make such kind of proposal. So Subaru cannot.
Are you able to search for activity of the centaurs?
Mm-hmm. Yeah.
You must have done that, right?
No, not really.
Then you look at the PSF.
Yes. We just look at some image, but that's not so clearly see.
Actually, I have a code to doing that. So I'm using the HSC LA archive data to test my code. Yeah.
Yeah, please do it. There is many main belt asteroid too, so you can search that main belt comets also.
Yes, I had searched for the Themis asteroid and find nothing.
Yeah.
Yeah.
But Yuchi has been doing that for the last 10 years and hasn't found anything. But the centaurs may be more interesting, Yuchi. I mean, if you don't find them, still, if you don't find any activity, there's still a good results.
Yes. So I investigate the right curve of centaur, but the only 30 centaur was found, and usually that we can determine the period only 4% or 5%. So I determined the 3 centaurs rotation period, but that's not enough for any study.
And Zhongyi, you have a question for Fumi? Want to say hello to Fumi?
Hello, Fumi.
Hi.
Can you hear me?
Yeah.
So I don't know if I understand. The question is about the size distribution. So if how the size distribution can tell us the formation or the something. I might be miss this point. If we got the same distribution from the some group or some family, what they can tell, what do they can tell us?
If the size frequency distribution, you can see the same one. That groups underwent the same collisional history, or
But if I don't know if the size distribution, the one from farther heliocentric distance or near distance is the same, how can they move to different heliocentric distance? I mean, if we find the same similar one from the Jupiter and the other one from the TNO.
Created. So I think that capable TNO went inward and to become a Jupiter Trojan. So that the NICE model predicted, and that the observation also said some same such kind of migration.
Okay.
Mm.
But in the
Do you
main bell
understand?
family, how it is all the family I mean, I don't know yet. The size distribution for all the family we know are the same, are similar or different.
Each family, you are talking about each family.
Oh, I mean, like Vesta or the Sima star or something that the family we know from the main bell.
I don't know, because my investigation is only inner part of main belt and middle part and outer part, or something average out of such collisional family.
Okay, so you mean from the collision family point of view, their size distribution are similar, right?
Yeah.
Okay.
I think so, because they are anyway fragment of so.
Okay. Any other questions for Fumi? I think that the TNO's size frequency distribution is very flat. Means that it has less small bodies, right? Fumi-san.
Less small body, less.
Because in your R value.
R value, if that R value, this is flat, that means that index is 3. 3 means.
Okay, because I thought that when people look at the Pluto and Chiron's surface cratering size frequency distribution, they find that they're missing some of the small body. Some of small size craters are missing.
Oh, that's small one, less than 2 kilometers or something.
Yeah, right.
Oh.
Okay. Any other questions from the audience? If not, we would finish this session for now. I'm sure that we will wait for Fumi-san to give another talk in near future when you discover the planet 9, right?
Yeah, I hope so.
Okay, very good. Okay, Fumi-san, thank you and Merry Christmas and Happy New Year.
Thank you very much.